try and solve this tricky trig integral on the screen. And while you do that, I wanted to point out that there are 24 days left in this maths countdown series. So there's still a lot of maths that we're going to do, and we've already covered a lot of maths. I've been counting down from 100. So make sure you stick around as well to see what I'm counting down until. Right, let's turn our attention to this integral. So I would typically advise you to look for an identity that you can use to make some substitutions in here to simplify what's inside our integral, or maybe not simplify it, but re-express it in terms where it will be easier to integrate. Now, I won't recommend you do that for this particular integral, and it may be difficult to see exactly why, but I'm sure you'll see as I continue with the solution, I'm sure you'll understand why I haven't substituted in immediately. But just as a brief illustration, say for example I were to substitute in 1 minus cosine squared of x for sine squared of x over here, then I would be expressing my integral only in terms of cosine of x. And that's not very useful, because now when I'm substituting in for cosine of x, I also have to substitute in for the derivative of cosine of x, which is negative sine of x. And I don't have any sine of x's left if I convert this sine squared of x into 1 minus cosine squared of x. So you see that it's not exactly the best idea to go straight for that, or to jump straight into the process of re-expressing our integral. So what instead I'm going to do is I'm going to have this integral of sine of 2x times by cosine of 2x times by cosine of 2x. So I just split this cosine to the 4th power of x into cosine squared of x times by cosine squared of x. Okay, so this allows us to congregate those terms and to raise them both as sine of x and cosine of x raised to the power of 2. And then, of course, that's still multiplied by cosine squared of x. Okay, so that was a useful manipulation, because I know a double angle identity that involves sine of x and cosine of x, and I also know a double angle identity that involves cosine squared of x. And by using these double angle identities, I'll be changing my argument from x for both of these into 2x, so they'll be the same, which is useful for later on when we're trying to solve. It's nice to have all of your trig ratios with the same arguments or the same angles. So that'll be useful. And also what that'll mean for us is we'll have something to the second degree, and we'll have something to the first degree. So now we'll have an even power and an odd power, which makes the substitution easy as well. So if you didn't quite catch that, then I'll show you now exactly what I mean. So we know that sine of 2x is equal to 2 sine of x times by cosine of x. But I just have sine of x times by cosine of x, so I divide through by 2. Okay. Now for cosine squared of x, we know that cosine of 2x is equal to 2 cosine squared of x minus 1. But now I need to isolate cosine squared of x. So I get cosine squared of x is equal to cosine of 2x plus 1 all over 2. All right. So if I re-express my integral in terms of these double angles, I get the integral of, now for sine of x, cosine of x, I'm substituting in this. So we have sine squared of 2x over 4. You can see I raise that to the power of 2. And then for cosine squared of x, we have cosine of 2x plus 1 over 2. Now, it's useful whenever you get constants to take them out your integral as soon as possible. Not in all cases, but in this case it is useful. So 4 times by 2 is going to be equal to 8. So we can take out 1 over 8, and we can get rid of these denominators. All right. So what do we do now? Well, I'm going to distribute the sine squared of 2x into this brackets. So we have 1 over 8 to the integral of sine squared of 2x cosine of 2x plus sine squared of 2x. And I'm sure you can already see that this is going to be much easier to solve than our initial integral, or than if we had to have made a substitution for some other identity right at the start. Okay, and another important thing to note is we have our arguments are all 2x. Now it's particularly useful over here, but it's not necessarily beneficial that this sine squared of 2x has the same arguments as these, because I can split my integral up, and I will split my integral up. So what I'm saying is I can split this up into the integral of this plus the integral of this. However, I mustn't forget to distribute this 1 over 8 to both integrals. So I move that up, and I have 1 over 8. And now I can solve these two integrals separately. Okay, so for the integral on the left, we're going to let u equal to sine of 2x. So then the derivative of u in terms of x is going to be cosine of 2x, and then using the chain rule, we do the derivative of what's inside, which is the derivative of 2x, so times by 2, and that's dx. Okay, so if we carry on just with this left-hand integral, we'll have 1 over 8 into the integral of, now for sine squared of 2x, we're substituting in u squared, so we have u squared, and then for cosine of 2x dx, we will substitute in du over 2. Okay, but now I said we can take out this constant, so we get 1 over 16 into this integral. Alright, so but before we carry on with this, let's revert our attention back to this integral. So what identities do I know that can make this easier to solve? Well, I know that cosine of 2x is equal to 1 minus 2 sine squared of x. But now you might say to me, well, this sine squared has the argument 2x, whereas this sine squared has the argument x. And that's not a problem. I can simply substitute in 2x for our x. So if I substitute in 2x over here, I get 2 times by 2x, which is 4x. Okay, and then if I isolate sine squared of 2x, what I get is 1 minus cosine of 4x over 2. So now we add 1 over 8 into now this integral as opposed to the integral of sine squared of 2x. So we have 1 over, or rather let's say 1 minus cosine of 4x over 2 dx. Okay, but I can take that 2 out, it's a constant, and so I have 1 over 16 into the integral of that. Okay, so carrying on with our integration, we have 1 over 16, and then the integral of u squared we know to be u cubed over 3. And then if we turn our attention to this integral, we have the integral of 1, which is just going to be x. So it's 1 over 16 times by x, or just x over 16. And then the integral of negative cosine of 4x is going to be negative sine of 4x divided by the derivative of the argument. So that's divided by 4. And then, of course, that's still multiplied by what was outside. And then don't forget the constant of integration plus c, because we now have no integrals left over. Okay, but now we need to express this in terms of x. So we let u equal to sine squared of x, or sine of 2x. So now for u, we're going to substitute back sine of 2x. So we have this is equal to, and now 16 times by 3 is 48. So we have sine cubed of 2x over 48 plus x over 16. And this is minus, and now 4 times by 16 is 64. So we have sine of 4x over 64, and then plus c, our constant of integration. And that's the integral solved. So I hope you managed to solve this integral by yourself. And of course, if you did, well done. Thank you for watching, and I hope you found this video useful. And if you did, please don't forget to leave it a like and subscribe to my channel.